Hi students, in this final video for online lecture 5, we are now going to talk about some of the fundamental rules of electron behavior. So one of Bohr's biggest mistakes was he stated that all of our orbitals are going to be dependent on one value only, that value being the principal quantum number. This is how he did the Rydberg equation and many of his assumptions and led to his idea of the orbit or spherical nature of all atoms. This was a huge mistake. For all of the work that Bohr did and gave us many important ideas about emission spectra and just overall electronic properties, the idea that the energy is solely specific off of the principal quantum number is wrong. The reason why it's wrong is that when he was doing this, he was only using a one electron system. So there was only one electron within one orbital which was in one shell. So he believed that the electronic behavior was that way. As you start to go to the multi-electron systems, you are now going to see that it's not just going to be based off of n equal to 1 or n equal to 2, even n equals 3. We are now going to go to our reality. In a multi-electron system, the energy not only depends on N, but is L as well. So you will now see that they are starting to stagger. This is because the 2p orbital is going to have a slightly higher energy than that of the 2s orbital because of its electronic characteristics that we described back in the last video with our nodal planes. So as you can see here, my 1s orbital, which was correct in the Bohr model, now is dependent on n equals 1 and L being equal to 0. There is no secondary quantum number, so that's why he got it right. But now let us look at our 2s. If I have a 2-0 subshell, notice that that is going to have a different energy than that of something that is 2-1. This means that I have a different subshell, and the subshells have different energies. So back in the idea of the Bohr model, he was saying that only the shells have different energies. In the case of the multi-electron in true state, we are going to have our subshells having different energies from each other, and now the orbitals are going to have the same energy. This can be true for most things, but as you go into further chemistries, you will see that even sometimes the orbitals have different energies. So now we'll go to 3-0. Notice that we have gone up in principal quantum number. That is why we're getting further away, higher in energy. But as you can see, we now get to our 3-1, and notice that our p orbitals are higher in energy. The biggest thing is that you will see that I can go to the 3d orbitals. This gives me a principal quantum number of 3 and a secondary quantum number of 2, but you'll notice that it's actually higher in energy than that of my 4s electron orbital set. So this is the reason why, as that we are going to be filling these diagrams in the next chapter, why we are going to fill the 4s orbital before the 3d subshell because of the energetics that we are going to see and their stability as well as their electronic properties. So here is the modern periodic table. It's important that you see where some of this electronic data is stored. So as I said in the last video, the principal quantum number is located as the number on the far left side of the periodic table, because our principal quantum number talks about the distance away from the nucleus, and this is showing us that as we get our bigger number, our electrons are inevitably getting farther and farther away from our protons and neutrons. So this is the first indication that we have of any electronic behavior in our periodic table. The next thing I want you to notice is how the periodic table is organized. We have blocks, and these blocks are based off of the subshell. As you see here in the gray, this is what we typically call the S block. This means that the second quantum number, regardless of the first, is a 0. So if I have a 1s, it would be 10. If I have a 2s electron, it would be 20, 30, 40, and so on as I go descending down the periodic table. If I go over to the green, and you'll notice that I have the p block. Any electron that's put in for this location would end up having the numbers 1 as its second principal quantum number. So in this case, if I were to have a 3p electron, I would end up having to guarantee a 3, 1 first two quantum numbers. And then, of course, I would be allowed some variety of -1, 0, and 1, but I've at least told you where that subshell is. So as you can see here, our horizontal rows tell us the principal quantum number, then the chunks and blocks that they are in on the periodic table tell us the orbital type. As you can see for our d orbitals here located in blue, our second quantum number must be A2. So our secondary quantum number. So if I want to go and have 5D, the principal quantum number is 5. Our secondary quantum number must be a 2. Finally, for our f orbitals that you see at the bottom of the periodic table, our second quantum number must be a 3. So this means that we are allowed to have numbers of 4, 3 and 5, 3 are our only possibilities. So now let us go look at this example. We want to list the values of n, l, and epsilon l for the orbitals in the 4D subshell. So I need to go and write all mathematical possibilities, but I am limited in some cases. So if I have a 4D subshell, I am allowed a principal quantum number of 4. If I were to change that number, I'm no longer in my 4 shell, so I would not be able to have a correct answer. So now let's look at our available possibilities of L. Based off of our quantum number rules, I am allowed 3, 2, 1, and 0. But remember in our last video, we talked about how the second quantum number determines the specific type of orbital. If I need a d orbital, I am only allowed to have the number 2. So every one of my answers needs to start with the value of 4, 2. Now I'm allowed a little bit more variety. Because I have a second quantum number of 2, this means that I am allowed to have -2, -1, 0, 1, and 2. This means that I am allowed 5 different orbitals in the d subshell, and here are those 5 possibilities. So if on an exam, I were to ask you to give me one set, if you gave me 4, 2, -1, that would be a correct answer. If you gave me 4, 2, 1, that'd be a correct answer. Any one of these 5 answers would be correct. If you gave me anything else, you would be describing a different subshell. So now let's talk about a couple of very important rules. The Aufbau principle is how we state and go filling up electrons from their lowest energy orbital. This means that as we add electrons, we must go and put them in the lowest available spot. So notice that I'm going to put 1 electron in the 1s orbital. So what does that mean? Well, now I need to go and add a second electron. I can either add it in the 2s, but I am going to actually add a second electron in here, flipping its spin, making the last quantum number the only change. And now I have a full orbital. So the first electron that I drew would have been 1, 0, 0, positive 1/2. In this case, now I've drawn 1, 0, 0, and the only change that I made was flipping our electron's orientation. So now if I want to go to the 2s, I am able to do that and place that here. But seeing that our 2s is still lower in energy than our 2p, I need to put my next electron here. So if I go to the 2p, I can put electron number 5, and I can start to populate the higher energy orbitals. But we need to now figure out what we're going to do. Am I allowed to buddy up the electrons here, or should I go and put the electron in the next orbital of a subshell? The rule that dictates this is called Hund's rule. Hund's rule says that the most stable arrangement of electrons in a subshell is the one in which we have the greatest amount of parallel spins. So as you see here, I have populated the first 5 electrons. What I can do is go and add an electron into the vacant degenerate similar energy orbital before I go and buddy this up. So if I look at my first electron that I had back here, we can all agree that this should be 2, 1, -1, and positive 1/2. Now, there could be some variation in the third quantum number, but the other 3 quantum numbers are fairly correct. So now if I go in and add this electron is going to have a difference of quantum number, not in the 4th quantum number, but this is going to now be 2, 1, 0, 1/2. So this means that I have changed orbitals, but I have the same parallel spin. Notice that I have 1/2 here and 1/2 here. So now we know that they are parallel to each other. If I go and add my third electron in, won't you agree that this one should now be 2, 1, and now what is the only remaining possibility of my quantum number for the third position? I've used -1, I've used 0, so now this must be +1, and this must also be 1/2. This is the explanation of Hund's rule. So what else I can do in here is what happens if I would like to go and add a down arrow? Well, now I would go back and look at the first 3 quantum numbers that I had of my original, and the only difference is going to be the sign on my 4th one. So now my red electron is going to be 2, 1, -1, -1/2. So it's really important that you see that making small, subtle changes about electron location are bound by rules of the Pauli exclusion principle, the Aufbau principle, and now Hund's rule. We are going to use these rules in a very fundamental sense as we are starting to put electrons in here, and we are going to do that over our next lecture. Have a great day.